Okay. So if you still have those 4.4 handouts that were initially labeled 4.3 because I accidentally gave it the wrong section number. So it's really handout 4.4. And there's a problem, so 4.4 continued. There's an example we didn't get through, example 3, modeling the average cost function. Okay, so still in 4.4, still talking about the first, or actually we're talking about second derivatives in this section. So remember, you can always analyze the original function, finding domain. You can find any intercepts and asymptotes if they exist. And then what you would do is you take the first derivative and you find all the important information the first derivative gives you. So what are the two things the first derivative does? It tells you where the graph is increasing or decreasing, and then you can also use the first derivative to find peaks and valleys, which we call the local max and mins. And then you can find the second derivative, and that tells you about the concavity, and then it also, you can use it to find where the concavity changes, i.e. the inflection points. Okay. So we're going to essentially just do that here for a business example. So say I have this cost function. So if you want, you can think x is the number of units produced, and this function gives you the cost of producing all x of those units. Okay. And what we're going to do is we're going to write down all the pertinent information and sketch a graph of the average cost function. And then we're going to be doing a little bit of this now in the next two sections. We're going to be maybe finding the absolute maximum value or the absolute minimum value. Now, if you're producing something, you might want to know where your minimum cost is, right? How many units do you have to produce to get a minimum cost of producing all those units? Okay, so let's go through this. 1600 plus 25x squared. Oh, wait a second, though. That's not really the function we're supposed to be analyzing. So pay very close attention to the wording. We're supposed to find, and this should say average as well. So we want to actually sketch a graph of the average cost function. Okay, so anybody remember how to build the average cost function from a cost function? Yeah, so you take the whole total cost and divide by x. So we're looking at the average cost function. Remember, we put this little bar on top for average. And the average cost function by definition is the total cost function divided by the number of units produced. So this is going to be 1600 plus 0.25x squared divided by x. Okay. And then Ollie, we're just going through the last problem from the handout from last week. Right. The 4.3 or 4.4. Well, it was labeled 4.3, and then I told you to change it to 4.4. Okay, so that's the average cost function. Okay, so first of all, anybody be able to tell me the domain of this function? Any problems in the numerator? I can plug anything in I want, right? The only thing I can't plug in the denominator is 0. And also it should make sense that, right, you can produce any positive amount of units, right? X represents the total number of units produced. And we're always thinking of producing positive units. So the domain will be 0 to infinity. Okay. And then technically there is because we're dividing by x, are there going to be any asymptotes? So what was the rule for what was the rule for vertical asymptotes again?
What makes the denominator 0?
Yeah, anything that makes the bottom 0 but not the top. So x equals 0 is a vertical asymptote. And then I don't think we're going to have any x-intercepts or y-intercepts for this one. Since the numerator is always positive, there's nowhere place where the fraction equals 0. And I can't plug 0 into the function, so there's no x or y intercepts. Okay, I can't plug in 0, and the function will never equal 0. Okay, and that's all the information you could get from the original function. So domain is positive real numbers. X equals 0 is technically a vertical asymptote. The graph will either, as it gets close to 0, go up forever or down forever. And you can't plug in 0, and the function will never equal 0, so there's no x or y intercepts. Okay, so that was really like step 1 in the analysis, right? So get all the information you can from the original function. And then what would step 2 be? You get all the information you can get from the... So after you look at the original function, what do you look at next? Yeah, now we can look at the derivative. Okay, so we're going to look at c bar prime of x, or we'll analyze the derivative. Okay, now what do I have to use to find the derivative here? There's actually a couple ways to do it, but as written, yeah, is that what you said, Ollie? Quotient rule? Okay.
Can we just pop that x up?
You could also do that. You could move it up as an x to the minus 1 and then distribute it through. So it's really your call. Is it okay if I skip the quotient rule and do the trick? Yeah. Okay. So if I want, let's maybe simplify this function. This is going to be 1600 x to the minus 1. So right, it's 1600 over x, which is 1600 x to the minus 1. And then what happens if I divide the second term by x?
You lose an x.
Yeah, you'll just lose an x, so this will be plus 0.25x. So I just divided both terms in the numerator by x, and then this way I just have to, this makes it a lot easier, doesn't it? Now I don't have to use quotient rule. So what's the first term going to be? I take this minus 1 and I bring it out front. So you get a minus 1600x, and then what does the new power become?
2.
You subtract 1 and get a minus 2, good. Okay. And then what's the derivative of the second term? The 0.25x just has derivative 0.25. Okay. And then if I was going to take another derivative, I would actually just use this to find the second derivative. But to find all the information I can get, I will just simplify this. This is going to be negative 1600 over x squared plus 0.25. And if you get a common denominator, you get, well, you'll get 0.25 x squared minus 1600 over x squared. Okay. Let me make sure I push play on the video. So again, what I did is I just wrote the x to the minus 2 as a divided by x squared. And then I multiplied the 0.25 by x squared over x squared and combined them to a single fraction.
Wait, on the final one, where'd you get the x squared for the 0.25 on the top?
So I multiplied this by x squared over x squared.
Why?
To get a common denominator, so I can write it as a rational function. This is that simplifying piece, right? So like I said, I'll use this to find the second derivative, but I simplified it so I can find the partition numbers. Okay. And then how do you find your partition numbers? It's where the derivative is either 0 or does not exist, right? Okay. So c bar prime of x equals 0 or does not exist when either the numerator is equal to 0 or the denominator x squared equals 0. So I was just getting a common denominator there. That's what all that work was. Okay. And then we can solve the first one. So what can I do here? First I can solve for x squared, right? So I can move the 1600 to the right. And then I can get rid of the 0.25 by multiplying both sides by 4. Or you can divide by 0.25, same thing. And I think we'll get 6400. Now typically when you solve for x squared you get a plus or minus, right? Except for why do I not care about the minus here? Go back to step 1. What was that, Nathan?
Not in the domain.
Yeah, right? Any negative x value won't be in the domain. So here I only need the positive square root of 6400, so I believe x is going to be, is it going to be 80?
Yeah.
It's really plus or minus 80, but again, we're dealing with a cost function. You can't produce negative units. That doesn't make any sense. And then what's the other partition number over here? Where the denominator is 0 just tells us that x equals 0. Okay. Now how many critical numbers are there then? So there's 2 partition numbers, but which one of those, are they both in the domain? Yeah, remember our original function was divided by x, so our domain is positive x values. So these are partition numbers, but this one right here is the critical number. So that's the place where you might have a local max or min. So what I can do now is I can make a sign chart for the first derivative. I'm going to put 0 on the left because that's where the domain starts. And I'll put 80 on the right. Now there's something really important about there only being one critical number, and you'll see in the next section there's a theorem that I can tell you about. If there's only one critical number, not only are you going to possibly get a local max or a local min, it turns out if there's only one critical number, it actually gives you an absolute max or an absolute min. So that 80 is either going to give us a maximum average cost or a minimum average cost. Now we can do the sign chart thing. Remember, here's the first derivative. The denominator is always positive, so I only have to see what happens in the numerator. I think it's pretty easy to see if you plug something like positive 1 in, 0.25 minus 1600 is going to be negative. So the first derivative is negative between 0 and 80. And then once you get past 80, what's probably going to happen?
It's always positive.
Yeah, this time it'll turn positive. Like if you plug in 100 for x in the first derivative, you will see that you get positive values. Okay. Now I'm going to start cataloging our information here over on the left side of the board. Okay, so what do we know? The domain is 0 to infinity. X equals 0 is a vertical asymptote. There are no x and y intercepts. The average cost is increasing on what interval?
80 to infinity.
Okay, right? So we know that if we produce if you produce anything more than 80 units, your average cost function will be increasing. Which is actually bad, isn't it? Because that means if your average cost function is increasing, that means the more and more units you produce, the more each unit is costing on average. So you certainly, I don't think, would want to produce more than 80. Otherwise, you're paying more and more to produce each unit. Okay, but it's increasing on 80 to infinity. And the average cost per unit is decreasing on the interval from 0 to 80. Oops. And then you have do we have a local min or max at 80? Yeah, think of it this way, right? Negative derivative means the derivative's decreasing till it hits a point, and then it's going to start increasing to the right. So you have a local min, which, and we're going to talk about this today, also the absolute min of C bar of 80 equals, so now I'd have to plug this into the original function if I want the local minimum average cost. Someone want to do me a favor and plug 80 into this? 80 squared 6,400, I think I got it. 80 squared 6,400, we already knew that from here. 6,400 times 0.25 is 1,600 plus another 1,600. So the minimum average cost per unit is going to be $3,200 per unit. If I make anything less than 80, or if I produce less than 80 units or more than 80 units, the average cost per unit would be greater than 3,200. So if I want to pay the least amount on average per unit, we have to produce 80 units. Okay. And then now I'd have to go in and do the second derivative stuff, just to get the concavity. So part of this I just wanted to do a review and plus also do an example in the business calc realm. Now we already did essentially do part B. Okay, the minimum average cost per unit will be $3,200 per unit. I don't know what we're producing. It's got to be something pretty expensive here. Yeah?
What if there was 2 critical numbers?
If there was 2 critical numbers, then you're not guaranteed that it would be the absolute minimum. Right? If there was 2 critical numbers, maybe the graph would have done something like this, for example.
And that's what we're going to learn next lesson.
Yeah, we'll kind of learn when there are absolute max or absolute mins. Okay, so we'll talk about when they exist in the next section. But if there is more than 1 critical number, you can't guarantee that each one would give you an absolute max or min. It's only in the case where you just have a single critical number that'll always lead to an absolute max or min. But if you have more than 1 critical number, we don't know. There will be a fix for it. It turns out that if your interval is a closed interval, then there will always be an absolute max or min. But the problem here is that's not a closed interval, right? It goes on forever. Okay, but since there's only 1 critical number, it'll give rise to the absolute minimum. We'll see when we do the graph too. I mean, it would make sense, right? You're always decreasing to the left of 80. So you had to be above this minimum value. And you're always increasing to the right of 80. Okay. So at 80, that had to be the lowest point. Okay. Because it's decreasing to the left and increasing to the right. And then now we can do the second derivative stuff. Now again, for the second derivative, I'm just going to use this form. It's a lot easier to take the derivative of this than the derivative of this with quotient rule. Okay, so let's find the second derivative. This would be step 3, if you like, for graphing. You analyze C bar double prime. So C bar double prime of x is going to equal, well, the derivative of the constant term is just going to be 0. And then the derivative of this, we just need to use power rule. The -2 comes out front, and then reduce the power by 1. So it ends up being -2 times -1600x to the, would it be to the -3 power?
Yeah.
Okay. And then -2 times -1600 is 3200. And then x to the -3 you can instead divide by x cubed. Now, numerator is always positive, right? It's 3200. If we're on the interval 0 to infinity, is x cubed then also always positive? Right? We're only plugging in positive x values. So this is greater than 0 on the domain. That implies this function is always concave up. Okay, and if you're always concave up, can there possibly be any inflection points? Right, it's not going to change concavity, so there are no inflection points. Okay, so I think we've got all the information we need to graph this function. It's always concave up. To the left of 80, it's decreasing. To the right of 80, it's increasing. Okay. And here we go. So let's think of a scale. And I think we only need the first quadrant because our x values are positive, and I believe our outputs are always going to be positive. So let me see, what can I do here? I think I can go by, let's just go by thousands on the vertical axis, right? We need to get to at least 3,200. So we might as well go by thousands. Okay, and then what should we do on the x-axis? Is 20 is probably okay? All right, so we'll go 20, 40, 60, 80, 100, and now we'll stop at 120. And remember, this is the dollars axis, so this is x, number of units produced. And then this is your average cost per unit axis. So you can write C bar if you want, average cost per unit. So those are our units on the vertical, average cost per unit to produce X units. What I can do is when 80 units are produced, we're up here at about 3,200. And I should have maybe picked a larger scale. And actually, I don't know if the end behavior is going to be infinite on the right. So I knew there was a vertical asymptote at 0. Okay. And since if we're starting at your minimum, it has to be going up to the left. It's got to get closer and closer to infinity as you approach 0 on the x-axis. And then on the right side, I'm not so sure. Where was the original function again? Was it 1600 plus 0.25 x squared over x?
No, it was just.
I don't have the original function in front of me. What was it?
1600 plus 0.25 x squared.
Okay, and then to get the average cost, we divide by x.
Yep.
Now, what's the limit of this as x goes to infinity? So you got to think back to end behavior. Is the power of x bigger than the power of x on the bottom? Right, you have an x squared on top. So what grows faster, the top or the bottom? The top is eventually going to grow faster, so it is going to go up on the end. Okay, so this, for all practical purposes, this is the graph of the average cost function. It's always concave up. It's decreasing to the left of 80, increasing to the right. Okay, since the numerator has a higher power of x than the denominator, the end behavior has to be infinity. That's just pre-cal too. I'm not even doing any calculus to know the end behavior. Okay, that's a fact we should all know coming in here from pre-cal 1. Okay, and then since the bottom was 0 at 0 and the top isn't, you know that the vertical axis is a vertical asymptote. And since the function has to go up as you go to the left, it has to be going off to infinity. Right? When you approach an asymptote, the functions either go up forever or go down forever. So that's a rough sketch of the average cost function. Okay, but oh yeah, sorry.
Well, why when you plug in 20 to that equation, do you get 85?
You get 85 when you plug in 20? Let me double check. Yeah, I did get 85. What did I screw up here? Oh, I see what I forgot to do. Do you know where I plugged in the 80? I accidentally plugged in 80. So 80 was the critical number, right? We
Oh, you
determined
took it back
that.
to the original.
I accidentally plugged that into the cost function.
Yeah, it needs to be.
So I forgot to plug 80 into this. Can someone help me out here?
I get it.
The ideas are correct, I just did a little arithmetic error.
I got 40.
Okay. So that makes sense because I forgot to divide 3200 by, or I forgot to divide this by 80. I accidentally plugged 80 into the cost function instead of the average cost. So this should have been $40 per unit. And can I fix it? Let's just go 10, 20, 30, 40.
Right.
That was my mistake. So at 80, it should have been 40. My bad. If anything, I just made it. When you're working with the average cost function, you need to be careful. You should almost throw the cost function away. Does that make sense, everybody? I accidentally plugged just 80 into the numerator and forgot to divide by 80. So I should have really got a minimum average cost of $40 per unit. That's why at first I was like, what are we producing? It's friggin' expensive to produce. I was thinking like, we must be producing some sort of car or something like that. Okay, so all the work was correct. I just accidentally plugged 80 into the cost instead of average cost. Okay. All right, so the reason I wanted to do this example was, again, in a lot of our applications, especially with profit, revenue, cost, or average cost, a lot of times you do just end up with a single critical number. Okay? And if there is a single critical number, because it's decreasing on one side and increasing on the other, that critical number will give rise to an absolute minimum value. If there's more than one critical number, you got to be careful. Okay? But we'll see that either today or tomorrow. Okay, so I do have the handout here. I do have I think I'm only going to do online homework for this section. There's probably plenty of problems, and I didn't really want to bog you down with too many problems. We could start moving those around. There. And then Sally, and you could pass one back to Ollie for me. I'd appreciate it. Okay, so today we're not going to see any business examples today. We're just going to take care of how to find absolute max and mins. Section 4.6 will be called optimization. We won't really be learning anything new at all. It's just we're going to take everything we learned in section 4.5 and apply it to our business models. Okay. So absolute maximum and minimum. Now actually, Chloe, since you asked, we're going to take care of the case where you might have more than one critical number. But we're going to be looking on closed intervals. Okay. So first of all, definition of absolute max and min. You can read the really formal definition. Basically, all this is saying is if there's a value of c, so the function value there is bigger than all the other function values, f of c is the absolute max. So it's just saying of all the points on the graph, it's the one that has the largest y-coordinate. Okay, that's just fancy math speak for that. And then the absolute minimum would just be, there's some number you can plug into the function, so it's less than or equal to all the other y-coordinates on the graph. That would give you an absolute minimum. Okay, so I'm not going to go into big details about the definition of absolute max and min. Okay, right? Even this example, right? If 80 is your c, this right here would be the point c, f of c, right? And the y-coordinate f of c would be less than or equal to any other y-coordinate, right? If that was just some other point x, f of x, is it pretty clear that f of c is less than or equal to f of x? Okay. So if your y-coordinate of your point is less than or equal to all the other y-coordinates, then it's an absolute minimum. Okay. So that's all the first definition is saying. It's basically just saying it's the absolute max is the largest y-coordinate on the graph, and the absolute min is the smallest y-coordinate on the graph. Okay, and then let me straighten this back out so we can catch this board a little better. There we go. Now, this one theorem is much more important, I think, than that first definition. So theorem 1, this is called the extreme value theorem. Don't worry, not going to prove it, not going to make you prove it. What it says is a function, actually let's write this down first. I'm going to draw you a picture, then I'll write the definition down. So what happens if you take a continuous function on a closed interval? So maybe we're starting at A and we're ending at B, and say these are my endpoints. And what does continuous mean again? I have to be able to draw the graph from one point to the other without doing what? Yeah, that's the kind of heuristic way to explain it, right? The layman's way, without all the fancy math notation of limits. Right, if it's continuous, I got to be able to draw that function without lifting my pencil. Actually, I wanted to do this a little lower. There we go. Okay. Well, what do you notice is going to happen? If it's continuous and on a closed interval, what are we going to achieve for sure? There's got to be some point then that is the highest point on the graph. And there also has to be some point that's the lowest point. Okay. Now this can happen in other ways as well. Basically the continuous part, just it's letting me know it's not going up forever, right? There's no asymptotes. There's no weird things happening to the graph. If I have to get from this point to this point without lifting my pencil, the graph is going to be contained. It's not going to go up or down forever. You know, other ways this can happen, the endpoints themselves could be where the max or min are. Like maybe I have a function that just decreases the whole time. Right? And then this would be the absolute max. And this would be the absolute min. Okay? So in this case, maybe the endpoints give you the maximums. In the previous one, maybe where you have horizontal tangent lines is where you have the max or min. Okay, but the point is if you're on a closed interval and your function is continuous, there has to be an absolute maximum and there has to be an absolute minimum. There's not going to be any weird things like asymptotes where the graph goes up forever. Okay, so that's what the extreme value theorem says. A function f that is continuous on a closed interval, and we just call it the closed interval from A to B, has both an absolute max and an absolute min. Now, why do we care as business calc in the business calc class? All of our basic functions, profit, revenue, cost, average cost, all these functions are going to be continuous on closed intervals. Okay? So, for instance, there'd have to either be, like if I took that previous example, if our absolute cost function, what if I told you that we could only produce between 20 and 120 units? Right? Instead of saying we can produce any number of positive units, if we have to work within a specific closed interval, there will be an absolute maximum cost and there will be an absolute minimum average cost. And I should have said averages. Okay? So there's a procedure here. Theorem 2 just says absolute extrema, if they exist, either occur at critical numbers or at endpoints. Right? So these two would give you critical numbers because the derivative was 0 there. Or maybe your absolute max and min are at endpoints. Or some combination of both. Okay. So what we do then if we want to find absolute max or mins, okay, we make sure the functions, so now I'm looking at the procedure here. You want to make sure that your function's continuous. If we're working with polynomials, then it's automatically continuous. Then you find the critical numbers in between the endpoints. And then step 3 is you plug in the endpoints into the function and all the critical numbers. The absolute maximum is the largest of those values, the absolute minimum is the smallest. So basically you just find the critical numbers in the endpoints, you plug them into the function, the biggest would be the absolute max, the smallest is the absolute min. So we're going to do this in, I don't know, maybe we'll do a couple intervals in example 1. How are we doing on time? So I'll have to finish this tomorrow.
We need a lot of space.
Huh?
For like these 3, will we need more space?
You will. Yeah, I just didn't have time again to actually fix this. So you'll probably need to get out a separate piece of note paper for fitting in these examples. Okay, so example 1. Let's say f of x is 2/3 x cubed plus x squared minus 4x plus 4. And again, maybe you can be thinking of this as, well, certainly not with these intervals since they include negatives. You know, maybe this is a profit revenue cost function or something like that. And we're going to find the absolute max and min on, we'll start with the interval from -3 to 2. I don't know if I'm going to get through all 3, but I'll do 2 of them. Okay, so what does the procedure say step 1 is? Make sure that your function is continuous. Now this is what kind of a function? It's a polynomial. And what do we know about polynomials? They're continuous.
All real.
Yeah, everywhere really. Okay, so I'll write it down. Step 1, f is a polynomial. So f is continuous everywhere. Okay. Step 2. Now it says to find the critical numbers in the open interval from -3 to 2. And what do I need to find critical numbers? So something is a critical number if what is 0 or undefined?
0.
Yeah, right? The critical numbers are where the derivative is 0 or undefined. Okay, so we're going to find critical numbers in the interval -3 to 2. So we'll take the derivative, f prime of x. It's going to be 2x squared plus 2x minus 4. And then, yeah, just to get back to what you were saying, Chloe, like, even if there's more than one critical number, if it's a closed interval, we'll still be able to find the absolute max and min. But if it was like an infinite interval and there's more than one critical number, you might be out of luck as to finding the absolute max and min. Right? Does this function even have an absolute max or min on its entire domain? No, right? On one end it goes up forever, on the other end it goes down forever. That's why I need to restrict the domain to a closed interval to ensure an absolute max and min.
Then on step 2, is it supposed to be brackets or it's supposed to be?
It's the open interval.
Open.
So if you look in the handout, right, step 1 says make sure it's continuous on the closed. Step 2 is you just find the critical numbers between.
Oh.
That's all that's saying. Since we're going to plug in the endpoints anyways, it doesn't matter if the endpoints are critical numbers. And then can we factor this?
Yeah.
Okay, 2 can come out. And then, does that factor further?
Mm-hmm.
So what would you get? You get 2 times...
X minus 1, x plus 2. Right?
Yes, that should be correct, because you're going to get -1 times 2 is -2. -1 plus 2 is the +1 middle coefficient. All of you okay down there? You can see that? Okay. I can always move this if I need to. Okay. And then what does that tell me about the critical numbers? The critical numbers, basically, let's look at the entire domain first, are x equals 1 and x equals -2. Right, so this function equals 0 when x is 1 or -2. Now, are both those in my interval? Are those between -3 and +2? Okay, so these are also critical numbers on that open interval from -3 to 2. Okay, so our function was continuous, it's a polynomial. We took the derivative and set it equal to 0 and got our critical numbers. What does step 3 say we're supposed to do?
Plug in your critical numbers in your
Okay, so now we'll plug those two critical numbers and the endpoints -3 and 2 into the function. So we have to do f of 1, f of -2, and then we also have to do f of -3 and f of +2. I'm going to be lazy and use my calculator. And you plug these into the original function. I think 1 is the easy one. You get 2/3 plus 1 minus 4 plus 4. So it's just 2/3 plus 1, because the minus 4 plus 4 will cancel when I plug in +1. 2/3 plus 1 is, I believe it's going to be 5/3. And then we can plug in -2, so fraction 2/3 times -2 squared, cubed, plus -2 squared minus 4 times -2, and then plus 4. Let's get the decimals too, just so we have a good idea what these are. So I got 32/3, which is approximately 10.7. The 5/3 is approximately 1.7. Anybody get the other ones yet at all?
F of 2 is 16/3.
16/3?
Yeah.
And then can you push that little arrow button at those just above?
5.3.
That's approximately 5.3. Anybody plug the -3 in the original function yet?
I got 7.
You get 7? Okay. Works for me. Anybody double check that one? If I hear a second person say it, I'll buy it. But with just one person, I'm going to check it. I got 7 as well. Okay. All right, so we found the critical numbers in the interval. Okay. And then we plugged those and the endpoints into the function. So what's my absolute max going to be?
F of -2.
Okay. So that on that interval, that's going to be the largest y-coordinate. If this was a profit function, that would give me the maximum profit. And then the absolute min